Hello, and welcome to this lecture on networks. My name's Richard Harvey, and I'm one of the professors here at Gresham College, and greetings live from Barnard's Inn, which is the HQ of the Gresham enterprise. And as usual, when you're talking about a big topic like networks, there's a lot of selectivity that goes on. So let me just sort of get that out of the way first. I'm not going to talk about everything, but I'm going to talk about what I think are some key developments in the development of the internet. And I thought I'd start sort of right at the beginning, as it were, with this fascinating record taken from the Library of Congress, which you might not be able to read on the screen, but it's the first one of Samuel Morse's telegraphs, which was sent in 1844, May 1844. He demonstrated the telegraph in the US Congress. And he sent a message to his collaborator, Alfred Vail, who was in Baltimore. And this was the strange words that he chose. What hath God wrought? It was his question that I think he took from, well, it sounds like Old Testament numbers, doesn't it? Which is the message he sent. And to prove it was received, Alfred Vail sent it back. He sent back the same message. That's an example of ARQ, which is an important part of the internet, which we will discuss in a moment. So that was sort of telegraphy, and I picked that out to point out that data comms, or data communication, is considerably older than the internet. But if we just spool forward to the start of the internet, then I've got a little clip of one of the pioneers of the internet, so-called fathers of the internet, a chap called Kleinrock. And this is him talking about how the internet first started. And I should say Larry Kleinrock is based in UCLA in California, and he's discussing the first link, really, of what was called ARPANET, and later went on to become the internet.
So our job simply was to type in LOG. Now, up at the other end, there was another programmer waiting to watch all of this. And we had a telephone connection between these two. Telephone connection so they could talk to each other. What happened is, Charlie typed the L, and he asked, "You get the L?" And the answer was, "Got the L." He typed the O. "You get the O?" "Got the O." He typed the G. "You get the G?" Wacko. The system crashed. This machine went down. So the very first message on the internet ever was low, as in lo and behold.
Yeah, so that was Leonard Kleinrock explaining how another rather portentous message was the start of the internet. And that was a communication between UCLA and an organization called SRI, so Stanford Research Institute. What Leonard also mentioned in that clip was that they were using standard telephony in order to sort of check whether this thing was working. And telephony and data communication using sort of telephony type circuits has a much older history than the internet. And I thought I would just sort of briefly draw your attention to the difference between the two types of communication. So on the left-hand side, your right-hand side, we've got what might apply when we're talking about a telephony. And telephony tends to be about streams of data, video, audio, and so on. And the order in which they arrive matters. That's what I mean by causal. So if we change the order of words in this sentence, it doesn't make sense. They have to arrive in the right order. But you can stuff the signals down a finite bandwidth and still not corrupt them very much. And indeed, some signal loss is tolerable in voice communication, which is helpful. You know, if there's some interruptions, you say, "I'm sorry, could you say that again?" So you can have or you can guess what was said. Data aren't like that at all, really. Data communications tends to be very bursty. You know, the computer doesn't do anything for a while, and then suddenly it needs to sort of dump huge amounts of data on you. The order in which things arrive, it might matter, but it It often doesn't. We just want the data. We don't mind whether the last page arrives first. It doesn't really matter. We're going to assemble it all at the other end. There's a benefit in having more bandwidth. We can send more data. We send it more quickly. Whereas, we've only got one telephone line. We've only got one telephone call to make. We only need a telephone line. We don't need any more for that. But data loss is generally intolerable in the computer world. So these sort of rather different ways of communicating caused a bit of a problem in the early sort of design of computer networks. So point-to-point communication between computers was well known. Generally what you would do is you would use a telephone line, sometimes called a leased line. And if you were a consumer, what you might do is you might buy one of these big boxes, which is called a modem. Don't know if you remember those. And this is one of the first. Well, I think this is the first British modem. Actually, it's called a Daytel modem Model 1A. It wasn't the first. The first one was probably something called a Bell Model 101. I didn't trust any of the photographs on the internet of the Bell 101. It seemed to look like a fridge, which didn't seem to me likely. So I've shown you this one instead. And if you were a consumer, you might communicate using something called a bulletin board. So you would dial up some remote computer, and you would read all the messages on the bulletin board, and then you might add your own, and then you'd dial off. It was a sort of blog, but you only had intermittent access to it. They're very, very important in the sort of mid-history of the internet. And for business-to-business communication, this was also quite common. If you had a business with multiple sites, you would lease a line, in this country from BT, or in the USA from AT&T, at vast expense, and then you would either permanently connect these two computers, or you would dial them up using a box that looks like this. And that was really what the telcos, the telecommunication companies, thought computer communication should be like, really. Partly it was technological. They had sort of invested heavily in what's called circuit switching, the idea of, if you think of old-fashioned telephone operators saying, who do you want to be connected to, and plugging you in. That's essentially how a telephone system works even now. And that circuit switching idea was dominant, but also the financials around circuit switching was dominant. Telephone companies existed to charge you by the minute for voice calls. They didn't really know what to do with data. So this was all sort of coming to a crunch in the sort of 70s, when people realized that there was the potential for computation. Before we get to the invention of the internet, however, I'd like to sort of call out a precursor to the internet that most people regard as sort of the precursor to the internet, something a network that wasn't the internet but is incredibly important and influential. And to do that, we have to zoom across to Hawaii. So the University of Hawaii in those days had I'm talking 1969 or so, had 4 campuses in Hawaii. And there weren't any leased lines or telephone lines that ran between them, that were easily obtainable lines. But there were radio communications. So the main campus, which is shown here in pink, had a mainframe computer. And what the scientists wanted to do was give remote people at the remote campuses access to that mainframe computer. So they devised this network called AlohaNet. The person behind it was Norman Abramson. Now, I should just point out, I mentioned Norman Abramson. I haven't mentioned the 4 or 5 collaborators who worked with him. That's really for want of time. Almost all of these developments were large team developments. So do go and consult Wikipedia, Google, or the usual sources if you want the full list of influencers here. Now, how did this work? Okay, well, it had 2 radio channels, and the first channel was very conventional. So they would send out a little message from the first station, which was where the mainframe was, and then that would radiate and it would hit all of the substations. So that's really easy. That's like broadcast radio. It's just broadcasting some data. No problem. Now, what about the return channel, though, or the backhaul, as it's sometimes called? Well, they only had 2 frequencies available to them, and one of them was used for the transmit. So all of the other stations had to share the other frequency. Now, they could have done it, as I've just drawn it on this slide. Did you notice that they didn't all transmit at the same time? It was as if they were in a sort of rather synchronized, early dance, after you, after you, after you. That's called time multiplexing, where you divide the time into slots and you say, your slot is here, and then your slot is here. That would have been a very conventional solution. The problem with time multiplexing, of course, is most of the time computers are quiet, so the slots are occupied, and then one of the computers has this desperate need to sort of burp all of the data all immediately, and it's only got one fiddly little time slot, so it's not very efficient, doesn't make efficient use of the bandwidth. Nevertheless, that would have been the conventional solution, or they could have used a different frequency for each station. That would have been another solution. That's called frequency domain multiplexing. What they designed was something that was really just heresy at the time. I mean, it's just complete heresy. What they decided was that it wouldn't care if the pulses overlapped. So if one of the stations overlapped with another station, of course there would be a great big mess and nobody would hear anything. You would just hear a sort of jumble of signals. It's called a collision in our parlance. But what would happen is both stations would then back off for a random amount of time and try again. So it's a bit like one of those conversations that you'll have with people and you both talk at the same time. You go, ooh, blah, blah, blah. Instead of doing after you, after you, after you, what you should do if you want to get efficiency is you should just throw the dice and you say, oh yes, you got a 1, I got a 6. Well, you wait 1 second, I'll wait 6 seconds, you win. Right, you go. Okay? Now, that random back-off was one of the innovations of AlohaNet, which we're going to carry forward, which we have carried forward to the internet. And this idea of what's called a contention network, where each party shouts for space, and if they get the shout, everyone else keeps quiet because they can hear them listening. That idea of contention has been taken forward on all of the networks across the whole of the known planet. Quite radical and quite interesting and rather anarchic. I mean, definitely a highly anarchic system. Okay, now, brief deviation. This problem of how to communicate in noisy or corrupted environments has actually been generalized into, well, it's now called the Byzantine generals problem. And to be fair, the Byzantine generals problem is a bit more general than what I'm talking about here. The true Byzantine general problem is as follows, which is there are multiple generals on your side, and they are all looking to attack. So in this case, the citizens here in blue are on the tops of a hill, and they wish to attack the enemy who are in pink at the bottom of the hill. If they coordinate their attack, they will win. Right? If they fail to coordinate, they will be slaughtered. So it's very important that they work out how to coordinate and attack properly. Now, in the general Byzantine generals problem, there are multiple generals, and some of them are turncoats, and some of them are liars. Okay? Now, you can see why it has to be called Byzantine generals. Leslie Amport, who wrote quite a lot on this problem, he was desperate to rename it because I think originally it was called the Chinese generals, which doesn't, it's not very flattering being thought of as a turncoat, is it? So he was going to rename it Albanian generals in the idea that there were no Albanians, Albanian being a closed society at the time. And then his friend pointed out there were lots of Albanians and they would be very upset. So it became Byzantine generals. Now, how does the Byzantine generals problem help us? Well, actually, as I formulated, the Byzantine generals problem does not have a solution. There isn't a perfect communication that can circumvent it, but I can illustrate one of the features that was also a feature of AlohaNet and has become a feature of the internet. And so it works like this. General 1 decides to send a message off to General 2. And General 1 knows, he or she knows full well that that message might be intercepted and it might be corrupted. So the message says something like, let's attack, at 5 o'clock this afternoon. And this general then acknowledges this message and sends it back. So in this case, so long as you have received an ACK back from the general which says, I acknowledge your message saying that we will attack at 5 p.m., then you have a little more security that you are both able to coordinate. Now, as I said, this is not a perfect solution. I mean, if you've got really Byzantine generals, of course, it might be a lie. Of course, they might have spoofed the message. But the ACK makes it much less likely that you will have a problem. Now, in general, this idea is called ARQ, automatic receive request. The idea that in order to have effective communication between two parties, you essentially repeat part of the message, or you acknowledge using some special signal part of the message, and it's a very important part of the internet protocol. And it was first developed in Aloha. Aloha, there are various ways you can deal with ACKs. On some mediums, like wires, you can listen simultaneously when you transmit to listen for collisions. So if you don't hear your own voice coming back at you, as it were, you know there's been a problem. On other ones, you use receipt requests. So you say, well, I sent this out, but I didn't get an ARQ. I didn't get an ACK back. Therefore, probably something's happened, so I'll send it again. So ARQ can work like that. Now, how does this all tie in to the internet? Okay, well, the internet has a slightly later vintage than AlohaNet, and it started with a network known as ARPANET, named after ARPA, which was the Advanced Research Projects Agency, which was essentially a way of the US military funding things that they thought important. And there have been various sort of conspiracy theories about why ARPA funded this network. They've all been denied. They weren't sort of, some part of global domination or anything like that. As far as we can tell, they funded it because they were funding lots of research groups in different parts of the US, and they got frustrated that they weren't communicating properly. And so they thought, well, we'll fund a network that allows them to connect. The early versions of ARPANET didn't use the protocol that we're going to talk about, but the real innovation was this protocol called IP, the Internet Protocol. And IP and all of the stuff associated with the internet has become, it's half about the standards and what you do, and it's half about the bureaucracy of how those standards are introduced and regulated. I think it'd be fair to say that lots of internet pioneers would be horrified to hear me use the word bureaucracy, and they don't think of themselves as bureaucratic at all. But the standardization of these protocols is very interesting and probably worth a lecture in its own right. What actually happens is these documents are published, usually in plain text like this, and they're called RFCs, requests for comments. Well, I suppose you could comment on them, really, but they are, in essence, a statement of what is going to happen. What's interesting about them is that they are a permanent record of what happened. They don't get rescinded. I mean, they might get replaced. And if that happens, you can track the replacement on the website of the IETF, the Internet Engineering Task Force. There's a fascinating lecture on YouTube actually about the bureaucracy of the internet and how it was briefly tousled away from the American from ARPA, who were responsible for it. Anyway, this is the RFC for IP, the Internet Protocol. And what IP does is it specifies the format in which data should be sent. And this is actually a quote from the most famous RFC in the world. And it looks like this. I'm sorry it's such a grotty figure. This is how they write them, and I think in the interest of sort of historic veracity, you can see the original. I'll just quickly explain it, because you can see some of the features of your own internet connection in these diagrams. So the first thing that comes is a number, and the number says, are we working with Internet Protocol version 4, which is almost everyone was until recently, or 6. If it's 6, it says 6. The next one is just a number that tells us how long the header is going to be. The next thing that I want to comment on is how long the header plus the data is. That's a sort of check, because if that doesn't add up to what you've really got, then something's happened. Then we've got some flags or counters as to whether something can be fragmented. This is quite important in the internet world. You can't rely on every part of the internet having exactly the same size of computer or machine. So you need a way of splitting the data into chunks. And that's another difference between the sort of circuit switched or telecommunications idea. Telecommunications tends to be associated with very rigid protocols, which everyone agrees. This is not a rigid protocol. This is a sort of marker saying, are you allowed to fragment this or not? I'll talk about this later. This is an example of forward error correction over here. This is a flag telling us whether this bit of data is to do with controlling the network or whether it's got data in it at all. And then this is an interesting one. This is how long this block of data is allowed to live in the network, usually measured in seconds. That's important for something like voice over IP. When you're trying to communicate with someone by voice, if your packets get lost in the network, they're not going to be delivered on time. So you just mark them with a time to live, and the router sees them and says, oh, no, you've been around too long, sorry, you're dead. And kills it, TTL. What's this one? This is an identifier that allows you to reassemble fragments if you need to. Down here we have some security options, and I'll talk a little bit about those later. And then it all ends on the end of a 32-bit block. And the bit that I probably forgotten to talk about, but it's the most important bit, is the source address and the destination address. Now, what is implicit in all of this, but perhaps it isn't obvious, is what this says is if you want to communicate on this network that we're calling the internet, your computer, should construct a block of data like that and attach it to the data that it wants to send. It's a bit like a postcard. It's got the information on the card that you want to send, and it's got the address on the front of it. And it just slings it off into the network, just like a postcard. Just as you don't particularly worry about how your postcard got to you, you don't worry how the post office chose to deliver it, you just worry whether it arrives or not. This is exactly the same idea. And this is what we mean by a packet of data. You'll see the word datagram used, which I'm not very fond of, but it is a popular word. Data combined with gram, as in telegram. So this is what the header of a packet of data looks like. Now, what does the actual data look like? Okay, well, a couple of observations about this before we move on. This is obviously quite complicated. You know, it's sort of fiddly and intricate, isn't it? You look at it and you think, oh dear, imagine writing a program to strip out all of that stuff. You know, it's quite sort of fiddly. And getting all of these fiddly bits together was the job of the RFC editor, who was a man called John Postel. He's famous for Postel's law, which is the way you should deal with these packets coming into a computer. And basically it says if they're a bit of a mess coming in, you should listen to them and try and work out what's been going on, but you should not send out packets that are malformed. Okay, that's Postel's law, which is the sort of famous law of internet engineers. Now then, the internet protocol is the simplest of protocols, and you can see already that it's got some issues. I mean, the first one that may be evident to you is, well, my computer's got lots of things going on. You know, it's got a web browser going on, and it's got music being listened to, and all those sorts of things. How do all these packets sort of get routed when they get into my computer? Well, to do that, we need some additional addressing. And so this is where the user datagram protocol comes in, which is the simplest protocol I could find. This yellow stuff, that's the bit I've just been talking about, so that's the header. So I've called it the IP header. What we've got down here in green are two additional destinations, and these are a bit like sort of, they're called ports. They are internal addresses within your computer. So, for example, port 80 is conventionally used for your web traffic. So if something arrives and it's got port 80 in here, then your computer knows to send it to your web browser so that your web browser can deal with it and assemble the packets into something meaningful. We've also got some additional stuff here, like how long it's meant to be and the checksum. There's quite a few of these little checks around the place you've noticed, and I'll talk a bit about them. And then comes the data. It doesn't specify what the data is. That's entirely up to the two computers that are talking to each other. Of course, there are protocols for certain types of data, web data and so on. Now, what about these checksums and checks and lengths and all that sort of stuff? Right, that's a fascinating topic in its own right. It's called forward error correction. And so here's the question. How do you know if some data in front of you has been corrupted? Interesting question, isn't it? I mean, what you would do normally if you were, say, an English reader is you would look at the text and you would say, this looks like gibberish. You're using your semantic understanding of the text to say, well, there isn't a word like that. Oh, I can work out what's happened. They've replaced an A, or they've missed this letter. That's a sort of semantic check. Computers don't do that, at least at this level they don't. What they do is they augment the data with checks and balances. The simplest check you can think of is something called parity. So you count up the number of ones in the data block. If it's an odd number, then you add a 1. Okay? I always get this the wrong way round. I think that's odd parity. Yes, correct. Or there's even parity. Oh, well, I'll make up the number to be even. Or you could sum the number of ones in the data. Right? That's called a checksum. So you could say, well, there are 500 ones in this data, so I'll write the number 500 into one of the checksum fields. In fact, there's an interesting set of codes that not only allow you to know that something's been corrupted, they carry enough information for you to correct it. How cool is that, right? That's a bit like that's a postcard that's got all smudged, and you give it a shake, and somehow it rewrites itself to be as it was written originally. They're very fascinating. There's a whole lecture to be written about those codes. They're called forward error correcting codes. The person who thought of them was a guy called Richard Harvey. And Harvey, an interesting man, he shared an office with Claude Shannon, the man who invented information. Now, I'm sure you've noticed so far that essentially this doesn't quite doesn't quite fit with what you're used to on the internet. I mean, what I'm describing here is something that sort of slings packets out, and they might come back, they might not. It's just a fire and forget protocol. And you might feel like that's happening sometimes on the internet, but it isn't. Mostly you've got reliable communication. So in order to do that, you need another protocol, and that's called TCP, right? Transmission Control Protocol. You'll often hear them said together in polite company, TCP/IP. Right? They go together like Morecambe and Wise. They're pairs. Now the TCP is like a bucket brigade. If you don't know a bucket brigade is a way that a fire service might put out of a fire. You form a great big long line of firefighters, and one gets the water out of here, and they pass the water from one to the other and pass it over that. I couldn't find a YouTube video of a bucket brigade, so I found something similar. So this is my sort of visual illustration of TCP. Perfect. Now, I'm not sure that's approved by British building practices, but you get the idea. And what's happening there is that there is some complex interaction between the members of the bucket brigade, over to you, and so on and so on. And that's what TCP does. TCP is an ARQ protocol. It has these acknowledges built into it. And it looks a bit repulsive, doesn't it, on the screen, but it's not that bad. This is the old IP header that I explained earlier, and this isn't a UDP header, this is a new header. It looks a bit like it. It's called a TCP header. Has these ports. These are where do you route it in your block of flats, if you like. But it has some additional features in here, namely an acknowledgement number. And TCP allows computers to what's called handshake each other. So this is an example of the famous three-way handshake that goes on at TCP. So TCP first, if A wants to communicate with B, what happens is A says to B, I want to communicate with you, and my sequence number is X. That means the number I'm assigning to the first one of my packets is X. And then B says back to A, yes, I acknowledge your sequence number is X. Thank you. That's the ARQ. That's the, if there are any Byzantine generals lurking around, that's dealing with interference and all that sort of things. And then B says again to A, and my sequence number is Y. And A says, I acknowledge your sequence number is Y. So we've got this treble sort of handshake going on. At the end of it, they've established communication. So now, when A or B sends a packet, it has this unique number in it, the sequence number here, and they can be assembled in the right order at the other end. So this is very important because it means that as far as the programmer is concerned for TCP, it's a bit like opening a telephone circuit. So you can now just fire packets at a TCP port and they get assembled as if by magic at the other end. They're not traveling through the network in order. Right? Far from it. Some of them are going via Moscow and some of them are going via, Miami. But they all get assembled at the far end. So as far as the programmer is concerned, you've got this easy-to-handle programming model. And that's really, I think, why TCP IP is so popular. Well, TCP IP originally was implemented on a system called an IMP. And this sort of thing on the right-hand side here, which is the size of a refrigerator, is the interface message passing computer, IMP. And it was devised by a very interesting company called Bolt, Beranek and Newman, who are now part of Raytheon, I think. BBN, or BBNM, they were given one of the presidential medals of honor under the last president, I think, the last but one president, Obama. And because they were so important, they were actually started as an acoustics company, and for various reasons, which you'll have to go and read about yourself, they got into the internet and were very, very influential and did some brilliant engineering at very short notice. But it's also been implemented over carrier pigeon. Okay, this is the only picture I could find of carrier pigeon. Short notice, this is Speckled Jim from Blackadder. So it's fundamentally this block-based protocol that gives a convincing impression of continuous data flow as far as programmers go. Right, ladies and gentlemen, you now know as much as you need to know, I think probably more, about TCP IP. Now, you've probably got some questions. I know I had when I sort of went through this. The first question is sort of, how does anyone know an address? Now, it's a bit like the post office question. How do I know your address to send you a letter? Well, you tell me it. And it is one answer. There's a central registry, is the answer to that one, called a domain name service. And the domain name service allows you to convert human forms of addresses like www.google.com into a number. What about these collisions? I haven't said very much about that. Well, I'll talk about that in a moment. And then another one that might occur to you is everything's in the open here. The data, the addresses, the ports. Anyone can listen and read. Isn't that slightly alarming? So here are my answers to those things. So the addressing protocol is not really very difficult to deal with. There's a distributed set of addresses, and the idea is that your computer is pointed at the nearest available set of addresses, and if it doesn't know the address, it asks another address server, and so on, until either it's not resolved or it is resolved. So that's an easy one. However, congestion. That is an interesting question, particularly as almost everyone on this call will have spent months recently on Zoom or Teams calls bemoaning their internet bandwidth and presumably, I was going to say, shouting at their children upstairs to stop internet gaming, but of course it might be the other way around. Maybe the internet gamers are watching this and they're shouting at their parents to get off a stupid Zoom call with work. So this is a map of the ARPANET as it was in 1984. It moved around a bit in the early years, and the eagle-eyed people might spot that poor old Britain isn't even on even on the network. We dropped on and off ARPANET in IP because we couldn't decide. A lot of Europe couldn't decide whether this IP thing was a good idea. And there was a bit of a debate actually earlier on as to whether the internet should be based on internet protocol. There was great suspicion about these contention networks. We didn't really like them and they're not very well controlled, and the telecommunications company didn't like them. Anyway, there's a little cluster up here in the left-hand side of the internet, which connects the universities of Berkeley in California, Lawrence Livermore Laboratory, and LBL, which I think it stands for the Livermore Berkeley Laboratory. LBL and Berkeley are about 400 meters apart, but they're connected by this bit of a circuitous route going by Lawrence Livermore. And there was a bit of a curiosity going on because in the 80s, the internet just died. The internet crashed. So I want to talk a little bit about that and what's happened. And in order to do that, I want to say a little bit about how TCP communicates using this ARQ protocol. So what you might imagine happens is when we're dealing with TCP is it sends off A sends off a packet to B, and B sends back an acknowledge. So you've got this to and flow of information. So this is an example of communication using a single packet window. And it's horrendously inefficient because the amount of time it takes for this packet to cross, say, the ocean or some satellite link or something, I could have sent more packets. So this is a terrible communication mechanism in the sense that, one side goes, hello. Oh, hello. Yeah. It's a great big pauses. So there's a tremendous pressure to not do this and to use larger TCP windows. That would be more efficient. So let's put, 4 of them together and only send back a single acknowledge when we get all 4. Now, we can do this with TCP because the packets are ordered, so although they might not travel like a little train, we can assemble them so they look a bit like a train. So that's a sort of practical proposition. And we often say that TCP, therefore, is self-timed using the acknowledgement signals. So larger windows make more efficient use of the link. But, and I'm sure you're ahead of me, the larger you send these bursts, the larger these bursts are that you send, the more you're sort of dominating the whole link. So the more likely it is that you're either locking out other people or causing congestion. And when you've got congestion, the way the internet works is you back off. So you say, oh, I didn't get an acknowledgement back. Oh, well, I'll wait for a bit of time and I'll resend the data. So it's a bit like one of those irritating people at dinner parties who keep telling you the same old thing again, because you failed to give them a positive acknowledgement. You sort of went, oh, yes. They tell you it again. Very irritating. My recommendation is to be more like the internet and say, yes, thank you, we've heard that long enough. That's a positive acknowledgement and might shut them up. So none of this was really sorted out, and in 1986 the internet crashed. And it was this guy, Vin Jacobson, who realised what was going on, and he produced this early little graph of the problem. And what he's got here, what he's plotted here, is the send time across one of these links and the packet sequence number. So TCP has sequence packets. So what you'd expect this is to go up. You wouldn't expect it to do this. This is a retransmit. It's, oh no, all the way back to packet 10 again. Oh, send in a packet 50. Oh dear, oh dear, oh dear, oh dear. And this had sort of essentially took quite a speedy link down to almost nothing. And that was the beginning of congestion control. And congestion control is a hot topic in the internet of today. I'll just sort of briefly explain how it works. The idea is that, so why don't we just start slinging data down the network? The answer to that is we don't really know how much bandwidth we've got available because it's a distributed network and it could change. So that leads us to an algorithm. And this is Jacobson's first algorithm. They're named after places. So this is TCP Tahoe. And it's an additive increase, multiplicative decrease algorithm, AIMD. So what you do is you start with a single packet, and you say, here's my first packet. And you get an acknowledgement back, and you think, oh, great, that worked. Next time I'll send 2 packets. I get an acknowledgement back, oh, next time I'll send 3 packets. Next time I'll send 4 packets. And we keep doing that until we reach the advertised buffer size of the receiver. And I don't expect you to remember this, but there was in the protocol a possibility for the receiver to say, this is how much data I'm expecting each time. So, and once that has reached that maximum buffer size, that's fantastic. And we're now throwing data down and we're getting good channel utilization, as people would say. We keep doing that until we don't get an acknowledgement back. The moment we don't get an acknowledgement back, we assume we've got congestion. And a sort of safe assumption with congestion is you had sole use of the link. So if someone else came along and caused congestion, there's now 2 of you trying to contend for the link. So let's halve the window size. So we'll give that other person 50%. It's a very sort of fair and socialist sort of thinking. So that tends to lead to a pattern of transmission and back off that looks like a sawtooth. You've got this increase and a drop, an increase and a drop. And you put all these sawtooths together, and that's how the internet, that's how it works. And when you're doing that properly, it's called riding the sawtooth. So if you hear people about riding the sawtooth, that's what they're talking about. They're talking about adaptive congestion control, beautifully adapting to the stochastic nature of the channel. Now, you might be saying, oh, come on, Richard, this is all very sort of arcane, and wasn't it all sorted out in the 80s? And it can't really be a topic for current conversation. But that's not true. It is very much a topic for conversation. So if you're wondering why your internet isn't working at home, there might be multiple reasons, but have a look at bufferbloat.net, which is a fascinating website run, I think, by Jim Gettis and Dave Tart, who are just sort of, enthusiasts, really, looking at congestion problems. And what they pointed out is this situation can easily occur even with modern congestion control. So let's imagine you're doing a backup from your computer to a server. So you're going to send out some packets, and those packets pretty much fill up the buffer of the server, and they fill up the channel. I don't think I said what a buffer is. A buffer is a queue, right? It's a block of memory that serves as a queue. First in, first out queue. Now, once it's got here, I'm sort of indicating that we've reached your modem. It probably has a big buffer in it as well. So as we start to fill up that big modem, the modem is communicating back to your computer and it's giving you acknowledgements. And at the moment, it's giving positive acknowledgements. It's saying, well, I'm not full. Keep sending me the data. Keep sending it to me. And your computer's loving this. It's just piling stuff into the data and as fast as it can go. So you're giving this very convincing impression of everything working perfectly. Meanwhile, you decide to do a bit of web surfing because it's taking a bit of a while to do this backup. Now, web surfing also takes place via TCP/IP. So that's got a bidirectional protocol. Both of you are sending acknowledgements. Opening a web page has quite a few little handshakes going on as what address is this then? And have you received this data? Yes, I've received it, all that sort of stuff. The trouble is, your buffer's full with all of this backup stuff. So your acknowledgements don't get through. And because they don't get through, the web server that's trying to communicate with you just says, oh, well, he must be on a bit of wet string. I'll just throttle back my bandwidth because I don't need to deal with you. So that's buffer bloat. And it's an example of how sort of dark buffers in the internet can cause havoc. And to be honest, they're not causing havoc with bandwidth. Bandwidth isn't really the issue here. Most people's internet connections are big enough. If you work out what sort of internet connection you need in order to be able to stream a Netflix film, do a Zoom call, do a couple of internet telephonies and a bit of gaming, you've probably got enough already. The problem is latency. And latency, which is these delays between people, that is what's buffer bloat is a latency problem, and it's caused by it because all of the data is sitting there in the queue waiting to get there. So if you want a quick analogy, you're going to a restaurant and there's a queue outside the restaurant. That's the buffer. And it doesn't look so big, so you say, well, let's get in this queue. Great. Then the maître d'hôtel sort of takes you from the head of the queue and weaves you into the restaurant. And in the restaurant, you discover there's this vast queue, huge queue. Well, you'd never have gone in if you'd known there was this huge queue. And you absolutely wait there for ages. Meanwhile, there are takeout orders, and those guys, I'm sure you know what happens with a takeout. It gets cooked, it gets put on the side, and by the time you get it, it's freezing cold. So they really need to be serviced immediately. They're the equivalent of your voice over IP packets arriving at this buffer saying, we need to get through. The buffer's full, the queue is full. So that's what's happening. Now, what's the solution to this? It's a very interesting one, and one that's very common to you. The solution is just as the solution with the restaurant. The solution with the restaurant is, one, not to have unscrupulous maitre d's who take people into secret queues, but also to put out a sign which says, we're full, go away, right? That's called tail drop. And tail drop is where we deliberately shorten the buffers and we just drop packets. As soon as we drop packets, the upstream version of the internet, your computer and so on, will realize there's a problem and they will throttle back to make sure that the buffers don't get overfull and the bandwidth control all works again. So dropped packets trigger the multiplicative increase. Tail drops I say it's fascinating because there's a very interesting book by Brian Christensen and others on algorithms to live by, which talks about how understanding computer science algorithms can help your life. And he draws perhaps rather stretched parallels with tail drop with other things. The one that I like is, your employer says when you go away on holiday, you should have an out-of-office reply on your email. And it will say something like, I'm sorry I'm away, enjoying myself. But your email will be attended to when I return. Right? That's the equivalent of a vast buffer. I don't know if you've ever returned from holiday to find 800 emails in your inbox. And you think, why did I promise to attend to these things? It's madness. What you should have said was tail drop. You should have said, your email will not be attended to. Right? Find someone else. Right? That is the correct protocol, and tail drop is an important protocol for a lot of things and is perhaps underused. Now, security. You've got these packets whizzing around between people, and they're human readable. So if that was all that was happening, two people connected via wire, we wouldn't worry. But in practice, there's often a third person, and they might be malicious, an interloper, like this. And so they might be not malicious at all. They might just be accidentally in the chain. And there's lots of ways, if you're interested in computer security, there are lots of ways that you can insert yourself in there. So if you're on a Wi-Fi network, for example, you set up something called a Wi-Fi pineapple. And a Wi-Fi pineapple is a Wi-Fi service that looks like the open Wi-Fi network that you thought you were going to connect to. So you're in an airport. It seems so long ago in the pandemic, doesn't it? You're in an airport, and you see a BT Open Zone or an AT&T server there, and you think, well, I'll connect to it. And it's not a genuine one. It's something pretending to be the AT&T server. It presents all the web pages, but it captures your data. It's called a man-in-the-middle attack. So what can be done about this? Well, the obvious sort of solution is encryption. So just sort of thinking about this packet structure again, we could encrypt this bit, which is the data, because people argue that's the bit that matters. Well, lots of things do that. When you use HTTPS on the website, that's what it does. It encrypts this, but it doesn't encrypt this bit here, the header. And that doesn't give you superb security, because it means anyone who can sit there can work out what's going on. So it's doing that is called traffic analysis. So the solution 2, which is often combined with encryption, is to control the routing. The internet is fundamentally sort of anarchic routing. The idea is that packets can go anywhere and you shouldn't worry about it. But a virtual private network, or a VPN, is an attempt to control the routing. And the way it works is you're not allowed to, or you're not encouraged to connect to the internet. You connect to a machine that is in some strong room somewhere, a virtual strong room, usually in your employer's basement. And this connection here is totally encrypted, meaning they can see that interlopers can see you're communicating with this machine, but they can't see any of the addresses that you're subsequently using because they are themselves wrapped in a packet. This thing strips off the packet and sends it out into the internet or wherever. So that's how a VPN works. It essentially rewrites the headers of your internet traffic, and then the service that you're trying to access sends it back to this VPN machine, and it then sends it back to you, and you then decrypt it. And it's hell on earth for a lot of employees, because these things are slow. In my experience, everyone says, "Oh, you use a VPN." Yeah, you try using the ones that most people have access to. They're really slow. But controlling the routing in this way is one attempt at security. However, I thought I'd talk about one that was just a little bit more current than the VPN. And to do that, I just need to sort of briefly explain something about how this routing works. So if you are in some remote country, and I've picked a country that happens to make great use of this technology, Syria. Syrians are very keen on this technology for reasons that you might imagine. Your packets go through a series of hops. So the other day I measured my path to Google from my house, and I measured 10 hops to get to Google, and it took about 6 milliseconds to get there, which is an appallingly long time, I must say. It shouldn't take 10 milliseconds to get to 6 milliseconds to get to anywhere, but you probably go up to the moon and back in that time, but that's what it is. This path is quite convoluted, and obviously you're worried about this path because anyone along this path could read your packets. And you might think that just asking for news from the BBC website is not a very, who cares? There are quite a few parts of the world where people do care very much whether you're accessing that news website. So the solution proposed is up here on the slide. It's called the onion router, or Tor. And you'll see people refer to Tor browsers, or it's sort of rather hagiographically referred to as the dark web. I'm not quite sure why it's the dark web, but it's used for security. The original ideas here were funded by the Office of Naval Research in the United States of America, and they needed a way for people in foreign territories that might be hostile to the United States to be able to communicate safely, even though the path might be controlled by others. And it makes use of a protocol called SOCKS, which is a proxy protocol. And what proxy does is it rewrites your internet headers to make it look like they came from that device. So I send, say, my web traffic to a proxy. The proxy strikes out my address, which is on the packet, puts its address in its place, sends it off, and when it comes back by a fancy bit of technology, it says, "Oh yes, I know that was one of Richard's packets. I'll send it back." So that's fine because a proxy can obscure the back of a chain, if you like. So that's good. But what about if the proxy is owned by some foreign power or somebody who wants to do you some harm or just listen to you? What can you do? This was the clever thing about the Tor. What Tor did was your computer, it has a path through which it's going to send its things, and it communicates with each one of these to get a secret key that allows it to encrypt the packet. So firstly, it encrypts its packet with the secret key for node 4, then node 3, then node 2, and node 1. Off goes its packet. It hits node 1. Node 1 removes the encryption and sends it on to node 2. Node 2 doesn't know about your computer at this point. It only knows it's come from node 1, and the only thing node 2 can do is strip off the encryption, and what it discovers when it strips off the encryption is yet more encryption. So if node 2 was captured by an enemy agent, they don't know who you are, they don't know where you're going, they know where this came from, but this also has to be captured by an enemy agent. So that's the basis of Tor. It's very tricky to capture the whole of this network. So you can see how it works. You just send off these packets, and the onion is the onion leaves of encryption. And these are quite long and convoluted paths, which is why Tor is quite slow thing to work. And eventually, in this case, our service gets a request for some news, and the whole thing happens in reverse on the way back. Great. And Tor is sort of it's highly disliked by a number of politicians who feel that they jolly well ought to be able to see everything on the internet. But often, and the American security services have themselves complained about the use of Tor for nefarious things. The irony is it's a curious one, isn't it? That a system developed by them has in fact become known for protecting people's privacy. It's a neutral technology in the sense that it has positive and negative benefits, but that's the basis of Tor. Now then, there seems to be a lot to me that I haven't talked about in this lecture on networks, and some things I regret not talking about. I hardly said anything about wireless, and wireless is really important. There's tremendous consumer pressure for wireless communication. Nobody wants wires dangling around their houses, but obviously the problems of congestion and security are much more serious when it comes to wireless, and they're not solved. There's a lot of work going on at the moment on better security and access protocols for wireless. Latency we have talked about. It's the Achilles heel of TCP. Things take a while. If you've ever tried to have a choir practice on the internet, it's a nightmare, because not only does it take a while for your audio to reach the other side, each person has a different latency, so you're all singing literally to almost to a different song sheet. I haven't talked about the Internet of Things, which is a fascinating topic in its own right. If you're interested in that, there's a very good Gresham lecture by Martin Thomas, which talks about the Internet of Things. It's perhaps a little bit gloomy. It says there are some security issues with IoT, and that's true as of now, but they might get solved. Security and privacy I've touched upon, but I think it's such a fascinating topic that it really deserves a lecture in its own right. And in fact, that is the topic of the next lecture, which is the future of computer security. If you want a primer on computer security, I thoroughly recommend a lecture by Tara Wheeler, which took place here at Gresham College a few weeks ago, and she was talking about whether these sorts of nefarious deeds can be considered to be war crimes. Thank you.
Thank you very much, Professor Harvey. My name's Simon Thurley. I'm the Provost of the College, and I've been scooping up a couple of questions for you. First of all, you will be amused to hear a piece of chat. Anna G. from the USA says, here in the US, sometimes it's the parents playing games online and the children attending classes on Zoom.
As soon as I said that, I knew it would be the other way around. I knew that it would be the other way around. It would be the kids doing Zoom and the parents playing Candy Crush. Yeah.
So here we have someone who didn't quite catch what you said, just wants a bit of clarification. What is the name of the lecture online about the development of RFCs or something, and something about being tussled away?
Ah, yes. So there's, I wish I could remember. You'll have to search on YouTube. There's it's the history of the IETF. It is a rather long presentation by one of the founder members of the internet, and I'm afraid the name escapes me, but I will post it in the chat when I get back home.
Great, if you could, that'd be fantastic. And the other question we have this evening is, what recommendations do you have for further learning about the underpinnings of the internet, including its technologies and their security?
Well, the RFCs, I mean, it seems bizarre to say read the RFCs, but they're very readable. And if you read them in historical order, they are super great. And that's what I went back to prepare this lecture, because what I discovered was there's a lot of people giving overly simplified versions of the internet, which is a bit unacceptable. So I recommend actually the RFCs. Start from there.
Professor Harvey, thank you very much.
Thank you.